Let's talk about something that sounds completely impossible. Imagine you need to perform delicate surgery on a pipeline that's actively pumping thousands of gallons of fluid every single minute. Well, it's not a hypothetical. It's a real procedure called a welded hot tap. And today, we're going to break down how engineers pull off this incredible feat without spilling a single drop. So, here's the problem, right? You've got this massive pipeline. It could be carrying oil, natural gas, you name it. It's running 24/7, and shutting it down is just not an option. It would cost millions or disrupt critical services. But you have to add a new branch line. How in the world do you do it? To really wrap your head around the stakes here, think about it like this. It's like performing open-heart surgery on a patient while they are literally in the middle of running a marathon. You're cutting into a live, high-pressure, and often flammable system without stopping the flow. There is absolutely zero room for error.
And yet somehow, engineers do this safely all the time. The solution is this amazing feat of planning and precision, and it's called the hot tap. Now, the official definition sounds, almost boring. The technique of attaching a branch connection to equipment or piping that is in service. But don't let that fool you. That simple sentence describes an incredibly complex process of welding, sealing, and drilling on a live system that has to be perfect.
Okay, so what does this whole thing actually look like? This diagram here shows the typical setup. It might look a little complicated at first glance, but it's actually a really brilliant step-by-step system designed to contain immense pressure. Let's walk through it together. First things first, you have to build a super secure foundation. A special fitting, custom-made for the pipe, is welded directly onto the live line. This weld is absolutely critical. It creates the first pressure-tight seal and is the base for everything else. All right, next up, a permanent heavy-duty valve gets bolted onto that fitting. This valve is the gatekeeper. For now, it stays closed, acting as the main safety barrier between the crew and whatever is flowing inside that pipe. And finally, the star of the show, the drilling machine itself is mounted right on top of the valve. It's basically a highly specialized drill press that can handle insane pressures. Before anything happens, this entire assembly gets pressure tested to make sure it is 100% leak-proof.
So the equipment is all in place. But here's the thing. Bolting all that gear on, that's actually the easy part. The real work, the stuff that guarantees this goes off without a hitch, happens way before anyone even touches the pipeline. It is all about the plan.
This table right here gives you just a small taste of the pre-flight checklist. Engineers need to know everything. What's the fluid? What's the pressure? The temperature? What is the exact metal composition of the pipe? Every single one of these questions has to be answered and verified before they move forward. And that's really the core principle here. The success of a hot tap isn't decided during the drilling, it's decided in the office, during the planning phase. It's all about exhaustive preparation. Okay, so the planning is done, the equipment is tested. Now for the main event. It's time to actually cut into that live pipe. So the operator carefully opens that big valve, and the pressure from the pipe floods the machine. The boring bar lowers, a small pilot drill touches first to center the cut, and then the main cutter engages, slicing cleanly through the steel wall, all while the operator is tracking its depth with insane precision. Once the cut is finished, that piece of the pipe wall, it's called the coupon, is captured by a special device on the cutter. The whole thing retracts, the valve slams shut, and just like that, the new connection is live. But, and this is so important, you have to get that coupon back. You can't just leave a chunk of metal rattling around inside a high-pressure pipeline. That would be a disaster waiting to happen. Now, this whole process is governed by a super strict set of rules. We've seen how to do it right, but what's just as important is knowing when you absolutely, under no circumstances, should even attempt it. And these are just a few of the red lines. Trying to hot tap a line carrying, say, an oxygen-enriched atmosphere or certain reactive chemicals isn't just a bad idea. It's forbidden. The risk of an explosion or a catastrophic failure is just way too high. These are not suggestions. They are hard stops. Let's just focus on this one number for a second, 400 degrees Fahrenheit. The standard says that welding on certain steel pipes above this temperature requires a whole separate engineering review. Why? Because welding on a pipe that's already incredibly hot completely changes the metallurgy and the risks involved. And here's another absolute rule, pulled directly from the standard. You never, ever perform a hot top on an existing weld. A weld is already a stress point. Piling the intense heat and stress of a new weld right on top of an old one is just asking for a catastrophic failure.
When you put it all together, you realize these rules aren't just red tape. They are the invisible architecture of safety. It's a framework built from decades of experience, some of it learned the hard way, that allows this surgery on a marathon runner to happen safely, day in and day out.
So, after diving into all this, what's the big picture lesson? What does the hot tap really teach us about modern engineering? Well, it shows us the power of human ingenuity to solve what seems like an impossible problem. But it also shows that ingenuity only works because of incredible precision, rigorous safety standards, and a deep sense of responsibility. Hot tapping is really a perfect example of how we manage the powerful systems that run our world.
And that kind of leaves us with one final thought. The hot tap is this amazing engineering marvel, but it happens completely out of sight. It really makes you wonder, doesn't it? What other incredible, high-stakes feats of engineering are happening all around us, every single day, just to keep our world running?